Hi, my name is Tom Heffel, and this channel is all about helping students learn chemistry. In this video, we're going to do problems of strong acid, strong base titrations. And what a titration is when you mix an acid and base together, okay, there's a chemical reaction that occurs, and then we have to look at the result of that chemical reaction and then determine the pH. So kind of like the setup that we have for this particular problem is that we have this beaker that has 50 milliliters of 0.3 molar hydrochloric acid inside the beaker. Okay? And then we're going to use something like a burette, and we're going to open up this burette that contains the same concentration, they're both 0.3, okay, molar of sodium hydroxide. And as I open this up, we're going to figure out the pH at different points of what we call a titration curve. Okay? So let's go ahead and get started with this problem. Let's talk about initial conditions. Okay? So before any sodium hydroxide is added, where are we starting as far as pH? Okay, well, in order to get the pH of a strong acid, all we need is its molarity. Okay, so if that molarity of HCl is 0.30, okay, we know that all of that's going to transfer over into hydronium ions and chloride ions. So all of this is going to go away because all of it's going to react and there's going to be nothing left over. Of course, that's going to increase the production of hydronium ions and chloride ions. But the part that I'm most interested in is the concentration of hydronium ions, because the concentration of hydronium ions will dictate the pH. So I'm going to end up taking the negative log of the concentration of hydronium, which is 0.3. And if I take the negative log of that, that answer comes out to be 0.52. So the pH here is starting out at a pH of 0.52. But what I'm going to do is I'm going to open up the burette and I'm going to let some acid come out. I'm going to let 25 milliliters of, I'm going to let some base out. I'm going to fill it up till where 25 milliliters of base hit the acid and a chemical reaction is going to take place. Okay, and we call these chemical reactions neutralization reactions. So some of this base, okay, is going to neutralize some of that acid. And we need to write a chemical reaction for this, okay? So the hydrochloric acid is going to react with the sodium hydroxide in a chemical reaction with a single arrow. Basically, hydroxide is going to say, hey, proton, I think you're kind of cute. Why don't we hook up and form some water, okay? And then the sodium and the chlorine will hook up to form sodium chloride. Okay, so this is the chemical reactions that's going to take place. And we're going to do a BCA for this as well, before, change, and after, because we got a single arrow. Everything's going to push to the right as far as it can possibly can. Okay, now, because we have a chemical reaction taking place where the acid's actually reacting with the base, okay, everything that we do with our BCA, it has to be in the unit of mole. Okay, so they have to have the moles of acid and the moles of base at the very beginning. Okay, so let's go ahead and calculate the moles of acid and moles of base using the molarity equation. So we know that molarity is equal to moles over volume. So if I do some cross multiplication, basically moles is equal to molarity times the volume. Well, let's do the acid part first. Okay, so this first part is going to be the acid. The molarity is 0.3, and I'm going to write that as moles per liter just so that you can know, okay? And then we got 50 milliliters. That 50 milliliters has to be converted into liters, so it's going to be 0.040 liters, and you see how the liters cancel out, and 0.3 times 0.05 is going to give us 0.015 moles for the acid. So I want to label this as the acid. And the acid here is hydrochloric acid. And we're going to do the same thing, but we're going to do that with the base now, okay? So to calculate the moles of base, same thing, which is the molarity times the volume. The molarity up here is 0.3, and that's moles per liter. But at this point, okay, we've only added 25 milliliters. So I'm going to come in here and convert that to liters, 0.025 liters. Still, the liters cancel out. And I'm going to be left with moles. And the amount of moles that comes out to be is 0.0075. And that's going to be moles of my base Okay, so we got the base here, an acid here, and that base is going to be NaOH. Okay, now I'm going to plug those things in here and here. Okay, so my moles of acid is 0.015, and my moles of base is 0.0075. And this is kind of like where we're starting with the chemical reaction. Okay, well, if these are in the unit of moles, and I have a 1-to-1 mole ratio, then the one that runs out first is just going to be the lower of the two, because this is reacting in that 1-to-1 ratio. So right now, the sodium hydroxide is the limiting reactant. It's going to be fully consumed. Oops. And if it's fully consumed, that means 0.0075 is going to react. And if I know how much sodium hydroxide is going to react, then I know all of them. Okay, because if I know the change of one of them, I know the change of all of them. Because if 0.0075 moles reacts, and it's a 1-to-1 ratio, well, then I know 0.0075 moles of this is going to react, which is exactly half of the starting amount. Okay, so half of it reacts, and if I subtract, the first half, what's remaining is the other half. And of course, we're going to make some water, and we're going to make some sodium chloride. And now we're going to analyze, okay, this system, okay? And when you analyze for pH, you always look for strong things first. And if there's no strong things present, you look for weak things second. And if there's no strong or weak things, it's going to end up being a pH of 7, okay? Now, a few things that I want to talk about before we do that analysis. And that is kind of like what's going on with the chemical reaction, okay? Now, we've labeled this as a strong acid, strong base problem. So I'm going to label this as a strong acid and a strong base. And it's going to form water and a salt. Now, this salt is going to ionize. And it's going to ionize into sodium ions and chloride ions. And we have to kind of figure out, does that have an effect on pH? Okay. Well, sodium ions is the conjugate acid of a strong base. Okay. If you have a strong base, then the conjugate is going to be negligible. So I'm going to write up here negligible acid, okay? And chloride ions are going to be produced. And chloride ions are the conjugate base of the strong acid. And if hydrochloric acid is a strong acid, then the chloride ion is going to be negligible as a base. So I'm going to write down here as a negligible base. So neither one of these ions, the sodium ions or the chloride ions, are going to have zero effect on pH. So really, there's nothing on the product side that is really going to affect pH. What really matters is what's left over on the reactant sides that matter, because we got strong acid and strong base. Remember, the priority is you're going to look for strong stuff first, okay? And if there's nothing present, then you look for the weak stuff. And if there's no strong or weak stuff, then the pH is going to be 7, okay? Well, in this problem, after the chemical reaction's done, there's still strong acid present, okay? So this is going to be the part that affects pH. There's no strong base. It has no effect on pH. The water has no effect on pH. And the negligible acid and negligible base ions have no effect on pH. The only thing that has effect on pH is going to be this strong stuff, and that's kind of like our top priority. So what we're going to do is we're going to take these moles, because remember, this is in the unit moles, and we're going to calculate the molarity of the strong acid that's remaining. Now, the moles that's remaining is now just 0.0075, because the sodium hydroxide reacted with half of those moles, okay? So half those moles are no longer, they're now in the form of water and sodium chloride, but the other half is still present, okay? So those 0.0075 moles comes down right here, and I've got to divide that by the total volume, okay? Now the total volume, I started with 50, but I opened this up and added another 25. So 25 and 50 collectively is 75 milliliters of solution, okay? Now we got to convert that over into liters. So that's going to be 0.075 liters. If we do our work here, okay, 0.0075 moles divided by 0.075 liters tells me that my concentration of my hydrochloric acid is now 0.1. It used to be 0.3, okay? But some of the sodium hydroxide reacted with it, and we had a little bit of dilution that occurs just by adding the two volumes together, okay? So the molarity is now 0.1. Well, if the molarity is 0.1, okay, the pH is no longer going to be 0.52, and I have to come over here to this side and erase out the 0.3s, okay, and plug in 0.1. We have 0.1 molar of hydrochloric acid present. It's going to shift all the way to the right. So basically this happens, okay? All of that's gone, and it shifts all the way to the right. And if I have 0.1 molar of hydronium ions, I'm going to take the negative log of that, okay? The negative log of 0.1, okay, is going to give me a pH of 1. And basically what we do is we kind of repeat this process for 48, 50, and 52. Okay, so the next three problems I'm going to do kind of quickly, but there's something special that happens here, and then this one gets a little interesting as well. So please wait to the end of the video to see how things change at 50 and 52. But go ahead and try to plug in 48 right here, 48 milliliters, which is 0.048 liters, and see if you can get the pH, okay? And so maybe this would be a good time to pause the video and do that work on your own. And when you come back, I'll be working on that problem, okay? So we're going to change this part to 0.048. Because now we're going to open this up, and we're going to add 48 milliliters, 0.048 liters. When you take 0.3 and you multiply it by 0.048, okay, you get the moles to be 0.0144 for the sodium hydroxide. So the acid is still 0.015, but the base is now 0.0144, okay? So it's still the limiting reactant, okay? So all of this is going to consume, and there's going to be nothing remaining. But if we know the change of one of them, then we know the change of all of them. And really the product side, I don't really care too much about, because there's nothing over here that's really going to affect the pH. But I do have to do this subtraction. 0.015 minus 0.0144 is going to give us 0.0006, okay? So when I analyze this at the end, I'm looking for strong stuff, and automatically I see no strong base, but I see a whole bunch of strong acid. Not a whole bunch, but at least it's still present, okay? So I have strong stuff present, so I'm going to calculate the molarity of that strong stuff. So I have 0.0006 moles, and I got to divide that by the volume. Well, what's the volume? Well, 48 milliliters plus the 50 is a total of 98 milliliters. And into liters, that ends up being 0.098 liters. So when I divide these two, I will get the molarity to come out to be 0.0061. Wow, this has really gone down a lot. So I come over here, okay, and I substitute out my 0.1 for 0.0061. Basically, all of this is going to go away, 0.0061, 0.0061. And what I want to do is I want to plug that in to calculate the new pH. And if you take the negative log of 0.0061, you're going to get the pH of 2.21. 2.21, 2.21. So if you got that, great job. Now let's move on to what we call the equivalent point. So I'm going to label this as the equivalent point, okay? And what happens at the equivalent point is that the moles of acid is going to equal to the moles of base. So let me do some erasing over here, and we will do the equivalent point. The way the equivalent point works is our moles of acid and moles of base are going to be the same because the moles are going to be the same. So if you look here, we're going to have 0.015 moles of both items. So 0.015 moles here and 0.015 moles here, okay? In this case, there's really no limiting reactant, okay? They're both going to be consumed fully. So there's not going to be any of this present, And there's not going to be any of this present, okay? And we produce our water and our sodium chloride. But really, none of these things over here have an effect on pH. So there's no strong stuff. There's no weak stuff because this is a negligible acid and this is a negligible base. So simply, the pH is going to end up being 7. It's really just the autoionization of water that's taking place, okay? So now, the equivalent point is not always a pH of 7, okay? It's only a pH of 7 when you have a strong acid and strong base titration because the salt that you create are negligible acid and negligible base ions, okay? So that's the case for the equivalent point. So it's pretty easy for strong acid, strong base titrations at the equivalent point. If there's no strong acid or strong base present and nothing on the product side affects pH, you end up with a pH of 7, okay? Last problem, okay, and that's going to be when we go past the equivalent point. So that's after 52 milliliters have been added. So let's go ahead and put in our 52 milliliters, which is 0.052 liters, okay? And when you multiply those two numbers together to get the amount of moles, you end up with the amount of moles being equal to 0.0156. So the acid is still 0.015, but now my base is 0.0156. So the limiting reactant is now changing, okay? The limiting reactant used to be the sodium hydroxide because it ran out first. Now the limiting reactant is going to be the hydrochloric acid. It's going to run out first, and there's not going to be any acid remaining, okay? So if 0.015 reacts, then we know that 0.015 of the base reacts, and there's going to be 0.0006 moles of the sodium hydroxide present, okay? Now, I really don't care about the product side, but if you want me to finish the chart, it would look something like this, but we know that none of this stuff really affects the pH. We're always looking for strong stuff first, and now we got strong base present. So we're going to calculate the molarity of the strong base. And what we did is we added 52 and 50, so that's collectively 102 milliliters, which is 0.102 liters. And when we divide these two numbers together, we get 0.00588. And this is the molarity of sodium hydroxide, which is a strong base. So up here, I have the strong acid equation. I can erase that now. And I'm going to write a strong base reaction because it's what's in excess. And sodium hydroxide will ionize into sodium ions and hydroxide ions. So I'm going to put 0.00588 here. And it's going to push all the way to the right. So this is going to go down that same amount. There's not going to be anything left over. And it's going to push all the way to the right. Sorry, this takes a little bit of time to kind of write down. But this time I'm interested in the hydroxide ions, okay? And if I take the negative log of this number, I'm not going to get pH. I'm going to get the POH by taking the negative log of hydroxide ions. So I'm going to put that number in there, and I'm going to get POH equal to 2.23, okay? And if I want to get pH, I got to take 14 minus that number, and 14 minus 2.23 is going to give me a number of 11.77. And this is how you calculate the pH at different parts of the pH curve. And if we made a pH curve of what we have here, this is going to stay down here around pH, 0.52 to 1 to 2.2, okay? And then all of a sudden, it's going to spike up and then level off. Okay, and our equivalent point is going to be right here at pH 7. And for this one, that occurred at 50 milliliters of base added to our 50 milliliters of acid. I hope you found this content helpful. Hopefully you feel much better about doing calculations between a strong acid and strong base titration. And if you did find this helpful, please give it a like and subscribe. And when you add that comment, it really does push out this information to other students interested in learning chemistry.